Okay, so let's resume. February 16th, there's no class. Actually, I just realized maybe that's a holiday, right? February 16th. The reason why there's no class because we are doing circuits, right? So we're gonna have our largest conference holding in that week. It's called EE631. So a lot of circuit people, including myself, will unfortunately be there. So usually I just cancel that class that week. Okay, so that'll be Monday. I think that's might be a holiday actually.
Yep, President's Day.
So it's holiday, right?
Yes.
Yeah. So sorry. So I don't even need to say this. So basically, just no class. Yeah. So February 16th, is that the Chinese New Year?
17th.
Oh, 17th. Yeah.
17th is the Lunar New Year.
Yeah. For some reason, that conference usually collide with the Chinese New Year, like every year. So it's an international conference. So a lot of times, our colleagues from Asia, they always complain. I'm just in my holiday, and I need to come all the way here. And when is the Super Bowl? Is that Super Bowl Sundays?
It's the week before.
Oh, the week before. For some reason, that conference just remind me two things: Chinese New Year and Super Bowl.
Yeah.
Right. So every year around that time, either we watch Super Bowl in the conference, in the lobby, right? We find a bar, or we celebrate Chinese New Year over there. All right, but if you can, I do encourage you to go to that conference. Another reason why I need to go there because every year I bring back, some of the state of the art. So basically the latest analog mixing circuits, especially in data converters. Oftentimes, that will influence what class project I give out, I hand out through this class. Not to ask you to compete with those state of the art. No. I'm talking about more like a trend, right? So if let's say the trend, the industry are interested in particular type of data converters, I usually would suggest you to choose that type for your class project. Just because I know a lot of you want to kind of get an industry job, right, in the future. So that will be directly relevant. Yeah. So far, I can tell you the SAR-EDC is still very popular. So in the past, a lot of students decide to do SAR-EDC also for that reason. Yeah, okay, so we'll see what this year, what people are publishing. All right, so now let's. By the way, I upload all these slides to the website. Do you guys see that in the price space? Okay. All right, so let's continue the second part of the signal processing, Z transform. For this, your reading material will be Oppenheim Schaefer chapter 3. Basically, at this point, all kinds of Fourier transforms, you kind of need to refresh yourself. Okay, this part is way too common, right? So you can use your textbook that you had, in your undergrad, or like I said, Oppenheim Schaefer is generally a good reference book. I'm pretty sure that there is a lot of tutorial online that you can just refresh your mind. All right. Z transform. Why do we care about Z transform? Okay, and again, this is to refresh your memory. The reason why we do the Z transform because we usually mathematically want to describe a discrete time system. We really just do that Z. Okay. The counterpart for the continuous time will be Laplace transform. So you guys probably, hopefully, still remember this, right? So Laplace transform in S, right? Laplace transform. So this is more for continuous time. Right? Whenever you describe a continuous time system, you do Laplace. Okay. All right, so this is the counterpart, basically the counterpart of Laplace as Z. All right, so for example, right, so if you do Z to the power of -1 in a discrete time system, that means one sample, 1 unit delay. That means one sample delay. Okay, so Z to the power of -1, that means you delay by one sample. What about Z to the power of -2? Want to guess? You have 2 sample delay. right? Remember, it's always all by sample, right? So yeah, so you have two samples here, and that's it. Okay, whatever the clock that you are assuming for your discrete time system, you know exactly what that means. If I tell you, okay, just divide by 2 clock cycle, you know what that means. Okay. All right, so Z transform is a very generalized transform in the discrete time system, just like Laplace for the continuous time. All right, so what you do is like in the time domain S of n, right? And we do Z transform, we do capital X of Z. Okay, X of Z. And then if you want to do the Z transform mathematically, it's basically just a summation. Okay, summation of the time domain sample, except that you're gonna scale with Z to the power of minus n. Okay, so you do this transformation, and then that whole expression is your Z transform. So X of Z is your Z transform. Okay. Just like Laplace, right? Laplace and Z, they are generalized transformation, right? You know, in order to understand in more physical sense, we want to convert to the frequency domain, right? Like you know, if you go to the lab, right? You look at spectrum analyzer, you read those grid. Is that frequency or that's a Laplace? You look at spectrum analyzer, right? You look at that, you know, it's only swept in the actual frequency domain, right? Nobody show you, oh, by the way, it's Laplace 0.27. And you look at that and say, what does that even mean? It means nothing, okay? So you have to convert back to the frequency domain, okay? So for the discrete time system, in order to convert to the frequency domain, we have this so-called discrete time Fourier transform, DTFT. Okay? All right, so we have to bridge them. Z transform to DTFT. How do we bridge them? We have this magic relationship. Z equal to exponential to the power of j omega. Just like Laplace. Laplace, how do I convert the Laplace to the frequency? S equal to, remember, how do I bridge? S equal to j omega. Right? So this is the concept. Okay, so S equal to j omega, this is the Laplace to the actual frequency. In the discrete time domain, Z transform to DTFT is that exponential function. Okay, so on the Euler plane, what's that exponential function? Hopefully this all bring back to your good memory when you were taking your undergrad class. Okay. If you remember from your class, this is basically unicircle, right? On the Euler plane, this is Z equal to E j omega, right? And then this is Z plane, you have a real part, imaginary part. If you look at the magnitude of E j omega, what's the magnitude? 1. It's 1. That's why it's unicircle, right? And this gives you the phase. So when omega equals 0, this is a 0 phase, right? 0 degree. So that's why it's 1. As you start to increase omega, you cannot see this rotate, and then eventually will come back. And just keep rotating. Okay, so that's just a kind of a refresh our memory. Again, you know, this is a Z transform. In the bottom is the DTFT. Look at these two equations. Are they so close? They are super close. In fact, if you plug Z equal to EJ omega, they are equal. Right, so that's just why DTFT and Z transform, that's how they link to each other. Okay. All right, so next we're gonna do one more connection. We have a discrete time system, we have a continuous time system. I'm trying to bridge the two. How do I bring the continuous time and discrete time together? How do I model a discrete time system as if I model as a continuous time system? We know discrete time system is basically a bunch of pulses, right? Sorry, not pulses, samples, right? So like delta function, you go to a sample and go back to 0. We know in physical world, it's impossible, right? Go up and in no time, it come back down. There's no way. However, the closest continuous time signal that will mimic, just like a bunch of delta function, will be a bunch of pulses. Do you agree? You see, when I have the symbol, I just, as if I have a pulse going up and going down, and here I'm gonna call this pulse width as a tau. Okay? So this I'm trying to approximate, right? I'm trying to mimic, to approximate this discrete time sample using some kind of analog waveform. And that analog waveform being the bunch of pulses, right? So let me ask you, so this pulse duration tau, do I want that to be small or I want that pulse duration to be large? Small, right? So I want that pulse duration to be as small as possible. Then I know the system that I'm trying to mimic or trying to approximate, that will be exactly the same as my discrete time signal. Okay, so that's the bottom line. So we're gonna model this signal, discrete signal, just a bunch of narrow pulses. And we know that pulse duration, right? That is a pulse duration. When they are very close to zeros, basically just like discrete time samples. Okay, so that's our background. Okay, and one more thing I want to say is that because I want to make it energy conservation. Okay, so whenever I make these pulses, I want to make sure if you integrate this area, think of that like energy, right? You look at this area, guess what? You want to make this area equal to that digital sample. Does that make sense? Right? So you know the height, you know, that digital sample is larger than if I integrate that area, small pulse area, the area should be larger, should be proportional basically, right? Should be exactly matched to that. All right, so that's the second condition. So not only I model that as a pulse, but I also have this area, so tau times xs of t, so this is the pulse, xs of t are the pulses, so tau times xs of t has to be equal to the sample signal xt of nt. All right. Let's do some math. So let's start from that energy conservation. Okay, so xs of nt times tau should be equal to the sample signal. So I'm going to divide the tau to the other side. 1 over tau xc of nt. And this is what I call that as energy conservation. Okay, I know that, you know, in the end I'm gonna model all that different pulses, right? It's complicated. So let's just focus on one pulse. One pulse. So this is one pulse that I'm trying to model, and this pulse width is tau. How do I mathematically model a pulse? Is there any math function I can do to represent a pulse?
Unit step minus unit step.
Very good. That's exactly right? So in math, we have a step function. What is a step function? Huh? What is step function?
Step function is u of t, where it's 1 for t greater than 0 and
Right.
0 for t less than 0.
Yeah, so usually, you know, greater than t equal to 1. If you're less than 0, it's 0, right? So step function. Okay. Very good. So any pulse, the real world, is essentially the subtraction of that two step function. Do you agree? Okay, so I'm gonna express this. Okay, so this will be xn, so nth pulse. Okay, n pulse, and continuous time t. This will be the value I know is xc of nt divided by tau. But I want to express this time pulse exactly, right? How do I express that exactly? So I think the Mamoudi suggests we need a two-step function. So I'm gonna call this step function as step. Okay, as step. S step of t is exactly this, right? So when t equal to 0, you will go up to 1. This is nt. So I'm gonna express this pose, that show pose, will appear at n times capital T, and then need to fall back at n times capital T plus tau. So far so good? So what I need to do is I need to shift. How do I do a time shift? So I need to subtract the time, right? So step function of t minus nt minus, what is my second pose? Sorry, not pose, sorry, the second step function. S step t, so I also need to do the time shift, right? So how much shift do I need? T minus tau. Very good. Very good. All right, so this is the continuous time signal. This is one pulse. I know this pulse will occur at n times capital T. Because this is a continuous time signal, can I do Laplace transform? This is continuous time, right? Do you agree? Even though, yes, you know, what we are thinking behind the scene is that, yeah, this should be represent just one symbol. But right now, I'm not saying that, right? I'm saying that, oh yeah, it looks like just a pulse, and that's exactly the mathematical expression. All right, so what's the Laplace? Can I do Laplace? Actually, I should ask. Can I do Laplace? Continuous signal? Of course, I can do Laplace. Okay, let's do Laplace. Step function. What's the Laplace transform of the step function? So let's start from that.
1 over s.
1 over s, very good. Oh, but I need to as time shift. So what is that?
Times the exponential.
1 over s times
E to the
e
The power.
to the power of,
J omega tau. Is it J omega tau?
hold on, j, if you want to do j, you already convert to the frequency, right? This is still Laplace, right? So no j just yet.
Oh, just S tau
Minus
minus
s
S tau.
times nt, right?
Oh, NT. Okay.
Yeah, not yet.
Yeah, if you do the Fourier transform, yeah, that will be exponential minus j omega nt. So you're right, yeah. But right now we're still in Laplace.
Oh, it's NT.
All right. So what about the second pulse? Sorry, not pulse. Second step function, Laplace. 1 over s times e minus s and t plus tau, right? Do you agree? So far so good? Okay, and that's it, you know, and the first one is just a constant, right? Xc of nt, that's just a value, right? Coefficient. Do you agree? Xc of nt over tau, they are just coefficient, right? It's nothing to do with time, so there's no s over there. Okay, so then just do some algebra exercise. You get 1 over tau times 1 minus e minus s tau over s. I'm just combining the terms, okay? Times xc of nt times e minus s nt. Okay, and then just to remind ourselves, this is just a single pulse, right? We are really just modeling just a single pulse. In the full version, how many pulses do we have? Infinite, right? So every sample we have 1 pulse, right? So we're gonna sum all this n from minus infinity to infinity. 1 over tau, 1 minus e minus s tau over s times xc of nt times e minus s nt. Okay. Does that look simple to you? It doesn't look very simple, right? Because whenever you see the exponential function, you're gonna have a headache. Okay, but so don't worry. You know, how do I approximate the completed math function. So we have this so-called Taylor series expansion, right? Okay, so that exponential function, right, looks complicated to me. So let's do Taylor series expansion on the e to the power of x. So what's the Taylor series expansion of this?
The summation from n equals 0 to infinity of x.
So all the different order of the x,
Yeah,
right? So
different
zeroth order, which is 1, the first order, that's x.
X squared
Yeah,
over
the
x squared over 2.
factorial plus blah, blah, blah. All right, we are engineer, we like something simple, right? So we don't like anything is too high. This exponential function that we are trying to approximate is actually this term, right? So exponential of to the power of minus s tau. Okay, what did we say about tau? Do we want the tau to be large or small?
Small.
Small, right? As small as possible, right? In fact, I want that to be infinitely small, right? Because that's where I can approximate to a digital system. Sorry, the discrete time system. Okay, so when tau is very small, that means x is basically small. If I look at this Taylor series expansion, which term can I ignore? All the higher order terms I can ignore, right? Because you told me that it has to be small. It better be small. It has to be infinitely small. So all the higher order gone. What do I have remaining? 1. 1. Oh, what's x? X is minus
S tau.
s tau. All right, this is equation 2, this is equation 1. So I'm just plugging this e to the power of minus j tau equal to 1 minus j tau. What do I get? So 1 cancel out, minus j tau times minus 1, so that's plus s tau, right? S tau divided by s and divided by tau 1. Congratulations. You make the same equation so simple, right? So what you get in the end, yes, you still have this infinite terms, but really that coefficient become 1. Basically, that's what it says. So what you have in the end, xc of nt times exponential minus s nt. Okay, this is our Laplace transform of this approximated discrete time system. Earlier we said that how do we usually describe the discrete time system? What transform do we use? Z transform, right? But then this is what we just derived using Laplace on this approximated discrete time system. Those two should be equal. Okay, that's this slide. This is your Z transform. We know it. This is what we just did. We just did, right? We do the Laplace on this approximated neural process. Okay, you tell me that these two should be the same. Okay, so how do I make it the same? You just look at this. So Z has to be equal to what? This is the power of minus n, right? So Z has to be equal to e to the power of minus. Oh, no minus, sorry. The minus is already here. Okay, so we need to be careful. Okay, so Z equal to what? E to the power of st, no minus. Okay, so, oh, actually, I already have this slide on the slide. Yeah, so Z equal to exponential of st. All right, so we are done. That's how we map between Laplace and Z transform. by that magic equation. So they are exponential. Okay, exponential function between the two, and that capital T. Yeah, what is that capital T? Period of samples, right? Because you have discrete time, right? Discrete time, you take a sample. Okay, don't forget, right? It's a capital T. Yes, it's time, but it's a spatial time, right? It's a period that you take those samples. Okay. Does this equation look simple to you? Maybe it depends. Yeah? You look at this. Oh yeah, only 3 variable EST, so it looks very simple. But if you think about the function, that's complicated, right? It's exponential function. Yeah. So again, a lot of times, we try to simplify all this analysis. Okay, the exponential, if you work out the math, you're gonna become very sophisticated equation. Oftentimes, it does not necessarily give us a lot of a good insight, and also make our system more complicated. Okay, so just like a lot of the engineering problem, we like to make it simple. Okay, so how about this? Let's do a first order approximation to that Laplace to Z transform transformation. All right, so let's start from the one we just derived. We said that Z equal to what? E to the power ST. Too complicated. Exponential function, I don't like it. All right, so let's do this. So let's divide into 2. Minus ST over 2. Okay, so if I do Taylor series expansion, you just told me, right? So Taylor series expansion, right? E to the power x is 1 plus x, right? If I can ignore the higher order term. If I can do that, you know what? You see, I get rid of the exponential function, right? So on the numerator, it will be 1 plus st over 2. On the denominator, what do I get? 1 minus st over 2. Much simpler, okay? And you can rearrange the variable. You get s equal to 2 over t times z minus 1 divided by z plus 1. This, again, transforming between the z and the Laplace. Okay, I know it's a ratio, but you look at the numerator, denominator, it's just the first order. Okay, first order approximation. This transformation is called bilinear transformation. Okay, so you probably have heard about this when you were undergrad. You probably just forgot. This is called bilinear transformations. This is how you essentially to map the j omega s's in the s plane to the unit circle of the z plane. If you go through this transformation.
The reason why we don't directly Taylor expand like the e to the power of st, but instead like use the division is to like make the approximation more accurate by lowering the weight of the secondary term.
No, it won't be more accurate, right? The most accurate has to be following this. It's just that when you plug in this exponential function, you just look at exponential and you don't have any insight. You will be stuck. You say, oh, okay, that's math, and yes.
I mean, just why can't we just write it like z equals to e to the power of st equals to 1 plus st?
1 plus st. Oh, you mean directly?
Yeah, like why do we?
That's actually a good point. Why not just do 1 plus st? Okay. Well, first of all, if you do that, you won't have this property. Okay. So j omega s is in the s plane mapped to the unit circle, so you won't be exactly that. And by the way, there's gonna be some useful property when you do this kind of transformation. Okay. Because whatever that stable system, if you do this, it will still be stable. If you do, however, just 1 plus st, you don't guarantee because you are not mapping this stereo omega axis to the unit circle of the z plane. Okay, so so even though this may sound like random, just randomly do this, but actually there's a lot of reason why you want to do this specific type of transformation.
This is more accurate, right? Because ST is now very small. So if you discard all the higher order term, it's
Yeah, but I think
This
her point
one-
is that
this one
we
is
do the
right.
same thing here because we also ignore the higher order term.
but that is over 2. And you have 2 terms. Yeah, you have the denominator and the denominator. So
Sure. Yeah.
Yeah.
So this for sure will be a little
more precise.
more precise.
accurate.
Yeah, it will be a little more precise. But I think that reason alone may not explain why you want to do this, right? So that's why I'm saying the bilinear transformation will have additional good property. Okay. So here's a question: why do we even bother to do this transformation between Laplace and Z transform? You probably are asking yourself right now, right? So who cares? The reason why we care is because a lot of electronic systems actually are well studied in the continuous time domain. For example, when you take all this undergrad electronic class, you learn about what Butterworth, Chebyshev, all those different filter. You know how to write in Laplace, right? You know how to write into Laplace transform, right? And they say, hey, I know all this 100 different type of a good analog continuous time filter, but I don't know how to design this discrete time filter. I don't. But I want to learn from what I already knew in the continuous time domain. What you can do, you know what? Just take that analog filter, whatever that you learn, okay, Butterworth or whatever you learn from that undergrad class, you know how to express into Laplace transform. All you need to do, how do I convert it into a discrete time filter?
Plug in.
You just plug in like this. Oh my God. Everything that you learn about analog filter, continuous time, in no time, I say, okay, by the way, if you do this bilinear transformation, I can come up with the equivalent discrete time filter, and you're done. Okay. You just plug in, nothing else. So that's why this is where different transformation property will come into play. How accurate you do this transformation, how close you can do. It will affect your discrete time filter, right? So this will be your discrete time filter, and that's a function of z, right? Because you do the z transform. Okay. So let's do our first exercise. Okay. By the way, it doesn't need to be filtered, right? In fact, a lot of times when people try to understand this transformation, it's actually using the integrator to understand. Okay. So this is the integrator. So let me ask you, in the Laplace domain, in the continuous time domain, what is the integrator? Laplace. If I say, okay, this is an integrator,
I'm 1 over S.
and I do Laplace, it's 1 over
S.
S. Exactly 1 over S. So you have 1 over S right here. If I have a continuous time signal, if I do integrators, if I integrate, what do I get? I get all the area underneath this continuous time signal, right? Okay. So now let's look at something we call the discrete bilinear integrator. Okay. By name, you probably can guess this using the bilinear transformation, the right. Okay. So this is the transfer function if you do the bilinear integrators. So basically, it's like a trapezoid, right? So you look at the adjacent samples. You look at this area right here. How do I complete the area right here? You look at the first sample, second sample, right? So those are the base here, the height, right? You add them up, divide by 2, multiply by the height, which is t right here, right? So this is just like a middle school, geometry, right? You really do that. And turns out that if you write this a function in time, you look at the transfer function in Z domain, you get this. Oh my God, what is this? Remember I told you previously, if you want to convert from the analog continuous time system to the using bilinear transformation, you just plug in, right? S equal to that, 2 over T Z minus 1 divided by Z plus 1. And you know what? That's exactly that transfer function. Okay, why do I go through all this trouble? I want to show you this is the perfect Laplace transform which is doing integrators. On the top is the approximated discrete time integrators using bilinear transformation. First of all, are you convinced this is also doing the integration? It is, right? In fact, it's a yellow one, right? So from very far away, you look at this, oh yeah, it's doing the integration. But if you look very close, does that doing the perfect analog integration? What's wrong with this kind of integration?
There are errors.
You see there's error. Where do those errors come from?
The signal itself.
Neglect term we.
The one that you just neglect, right? You say, oh yeah, I'm an engineer, I like everything simple, and I have to agree with you. I also like something simple. You ignore all those higher order terms, and you know what? That is your consequence. That's your consequence. Right? That's your consequence. All right, so let me highlight this. This are the errors due to approximation. Okay, all right. Okay, let me see if I can at least finish this slide. Okay, so this is just summary of a bilinear transformation. This is actually not random. I know my derivation looks kind of random, but it's actually not. This is actually a well thought after transformation by a mathematician, I think, or signal processing people. Turns out that if you do this transformation, one of the key things that stability will be preserved, which is very important. You know how much time you guys all spend, not just 526A, but also in all the electronic class, right? You say, okay, make it stable. It's not easy, right? So you finally make it stable. You don't want that just when you convert to the discrete time domain, it becomes unstable. Okay, so that's why bilinear transformations actually guarantee that. Basically the left half plane poles will map inside the unit circle. Okay, so that's why you can preserve the stability. And also another nice property is that the minimum phase is preserved. So that's why actually this is one of the very popular transformation. Okay. Yeah, I just realized I actually cannot finish the signal processing topic today. But I'm almost done. So I will stop here. I will ask TA to start upload the homework 1. I think some of the problem you don't, it's actually on the sampling, stuff like that. So you can start walking through some of the problems. Okay. All right. Any questions? Okay. If not, see you next week.